everybody, and welcome to a new open class. We are today in open class number 197. So we are getting really close to the 200 mark, where we are going to prepare something special for sure, but not yet there. So we are today in open class 197, and today we are going to be talking about 3D object detection using YOLO. We have already done some classes already with YOLO, but in this case we are going to apply it to object detection in 3D, which is something that we haven't done previously, and it's very interesting and very useful in the robotics field, especially. We will see it in a moment. So yeah, I hope that all of you are going to enjoy today's class and you can get something from it. So yeah, we are ready to get started. Then, as always, please let me know if everything is fine here in the chat, if you can hear me properly, if everything is correct, so that we can continue without any issue. Video and sound are good. I can read here from Gilbert. Okay, so let me then already switch to my computer screen so that we can start. I can start seeing the chat here. Let me do that right now. There we go. Okay, so let me have a look here at the chat. Let me open the open class screen. There we go. So hello everybody. Hello Diego. Diego says the volume is a bit low. You can increase the volume here. All right. So maybe you can touch it there, Diego, to have the volume a bit higher. Hello to Gilbert. Hello to Steven, Elias. So yeah, welcome everybody, and then let's get started already. Let's not lose any more time. So as always, the very first thing that you need to do in order to get started with the open class is to get a copy of the project, all right? Then how to do this? Very easy. All you have to do is to click on this button that appears right here above the chat, which says fork and open the class project. Okay, then everybody click here. I'm going to also myself click here to get a copy of today's project. This is going to take a few seconds, and then once it loads, you are going to be redirected here to the project main page, which is this one I have here right now, with the streaming panel here in the right side, all right, with the chat and everything, so that you can write your comments, questions, whatever you want here. And then here, this is going to take a few seconds. Here, basically, the project environment is loading. Yeah, so your virtual computer is being loaded. Then, in my case, I'm going to remove from here the streaming panel. Actually, I'm going to move it to another screen, because I still want to be able to read the chat and everything. Let me open it here in the iframe window. There we go. Okay. Hello to Pablo. Hello to Caroli. Hello everybody, and welcome. Yeah. So important, everybody that arrives. Very important. Let's all open the class project. Okay. And this is going to redirect you here to the project window. And besides this, let me also remind to all of you that a copy of this project, of this ROS project, is going to be generated here in your account. Yeah. So if you come here to the left menu and go to the My Projects option, yeah, here you are going to find a copy of today's class project, and this copy is yours, is in your account forever. Okay. So in case that you want to revisit this class next month, whenever you want, you are going to have it available here in your projects section. All right. Okay, then as you can see, my environment has finished loading here. Let me close all this. Then once the environment finishes loading, you are going to see here, you should see here the notebook of the class automatically opened. Okay, here is where you are going to find all the notes, all the explanations, example codes, commands to execute. Everything is written here in the notebook. Okay, so in case you get lost at some moment, you can come here and see what we are talking about, okay? Also all the details about the explanations, maybe I'm going to be skipping some parts, everything you're going to find it here in the notebook, all right? Then very important that you have your project copied and loaded before we get started with the class. So let me ask you right now, has everybody been able to open the project properly? Yes, no, any issue so far? My environment is still loading, a bit slow. Yeah, don't worry, just wait until it finishes. Yes, yes. It will just load eventually, just wait, yeah. Yes, 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 all good. Already working on it. Okay, Gilbert, as always, he's going a step further. %. Yeah, don't worry. It's going to eventually load. Okay? So think here basically what you are loading is a computer in the cloud, okay, with an Ubuntu system, ROS installed and everything, so it might take some seconds, okay? But it's going to eventually load, okay? So don't worry. Just be a little bit patient. All right. Then meanwhile, all the projects load, let me introduce the concept for today's class, which is 3D object detection, yeah? So what is 3D object detection in robotics? Well, 3D object detection is a critical task that enables robots to perceive, understand, and interact with their environment in a more advanced and autonomous manner, yeah? So unlike traditional 2D object detection, which we have done some classes in the past already. By the way, before continuing, let me point you that here, let me open another window, okay? So in case that you missed some of the previous classes, you can come here in the left menu to the self-led courses, okay? Here, if you come here and you click on the tab here in the right side, which says Open Classes, here you have access to all previous open classes. Okay, so in case you missed any of the previous classes, you can come here and check it out. For instance, here we have another class which we did on based on YOLO also. So in case that you want to check this out, you can come here and get a copy of the project and everything. Okay? Yeah. All right, then let's continue. So, yeah, as I was saying, so unlike traditional 2D object detection, which identifies objects in images or video frames, 3D object detection involves recognizing and localizing objects in 3D space, in three-dimensional space. Yeah? Then this process provides a richer spatial information, such as depth, orientation, and position, which is crucial for tasks such as navigation, manipulation, and interaction with real-world environments, yeah? So this is basically 3D object detection, and why it is so important in robotics, yeah? Then robots, yeah, especially those operating in dynamics environments, like the real world, for instance, need to detect objects not just as a flat plane, but in three-dimensional space to avoid collisions, manipulate objects, and interact with the world, yeah? 3D object detection is crucial in some of the following fields, such as autonomous driving, yeah, robotic manipulation of objects, or drone navigation, yeah, and many more, okay, many more. These are just some of the robotics fields where 3D object detection is crucial, is vital, right? Then how does 3D object detection work? Well, there are several key components that take place into this process. First of all, we have the sensors, yeah, which are the ones that provide the data, usually in the form of point clouds or depth maps, yeah. Some of the typical sensors used for 3D object detections are LiDARs, lasers, yeah, stereo cameras, depth cameras like a RealSense camera, for instance. For our case, for our class, we are going to be using a depth camera, okay? Which is already provided by our LIMO robot that we are going to be introducing in a moment, yeah? Then, besides the sensor, another key component here in 3D object detection are the algorithms, yeah? So once we have the data provided by the sensor, we need to analyze this data, process this data. And there are many different approaches here, yeah? Some of the common approaches are convolutional neural networks or region proposal networks, okay? In our case, we are going to be using YOLO, okay, which is based in neural networks. YOLO and Darknet, okay, for this class. And then finally, another very important component here are the bounding boxes, yeah? So once we have the data and once we have processed the data, what we do is to classify and show this data using bounding boxes, yeah? So the detected objects are represented with bounding boxes that provide information about the detected object, okay? All of this, we are going to be seeing it during today's class. Then here we have a bit of explanation about understanding YOLO architecture and its application in 3D space, okay? Now, this can be a little bit more technical, so I'm not going to enter too much into detail, but basically, I'm going to say that YOLO, which are, by the way, the letters for you only look once, is a real-time object detection algorithm known for its high speed performance and accuracy. Yeah? And unlike traditional object detection methods that apply several phases for object detection, yeah, YOLO attacks the problem as a single regression problem. It predicts bounding boxes and class probabilities directly from full images in a single pass through the network, right? Then there are several aspects in YOLO's architecture. First, we have the input, yeah? So the model takes an image and divides it into a grid. We have the bounding boxes. So each bounding boxes is represented by 5 predictions, where X and Y are the coordinates of the center of the box, W and H are the width and height of the box, and C is the confidence score. We are going to also see more details about this in a moment, yeah? We have the class probability. So for each grid cell, YOLO predicts the probability distribution over all the object classes. These probabilities are conditioned on the box containing an object. Backbone network. YOLO uses a convolutional neural network, yeah, a CNN, one of the methods that we introduced up here, yeah, the first one. As a feature extractor, yeah, in this case, the framework that we are going to be using for this neural network is Darknet, okay? But there are others. And then finally, the loss function, which is, so it penalizes, there are different also functions here, or different aspects in this loss function, including the localization loss, confidence loss, classification loss. Yeah, each one of them. So first one penalizes errors in bounding boxes coordinates, penalizes incorrect object, non-object classification, and penalizes incorrect predictions of class labels, in order to make the neural network learn in the process, all right? And yeah, so this can be applied, the YOLO algorithm can be applied in many aspects, such as autonomous vehicles, robotics, and augmented reality, okay? If you want more details about YOLO, you can check out previous classes or even to do some research on your own, but yeah, basically I want to focus this class not so much into the theoretical aspects of how YOLO architecture works, but more on the practice, and to provide you some tools so that you can practice with this directly in some real practical examples, all right? Then for this practical part of the class, we are going to be working on a simulation, yeah? On a simulation of the LIMO robot, which is this one we have right here. So in order to launch the simulation, all you have to do is to execute this command, right? And for this, we need a terminal, right? Then how to open a terminal? Very easy. You have to come here to the bottom menu in your project and click here on the first icon that you are going to find here, which says Web Shell, okay? Actually, it seems like this is... yeah, it was a little bit cut down, so let me reallocate a little bit this. Okay, I think now it's better because you can see my icons, right? Okay, yeah. Yeah, so this first icon that you can see here in the bottom menu, yeah, if you click here, this is going to open, as you can see, a brand new terminal, and then here all you have to do is just copy the command and paste it into the terminal, okay? As simple as this, all right? Then I'm going to execute the command, and then your processes are going to start here, and after a few seconds, we should see the simulation window automatically pop up here. So let me wait here for some seconds and see if I get the simulation. If it doesn't appear, we can also manually open it, but let's give it some seconds here. Okay. Yeah, everything seems correct. It's not appearing yet, so let me actually open it manually. So I'm going to, in case that your simulation doesn't appear automatically into the screen, okay, what you can do is to, again, come here to the bottom menu and click on this icon here, yeah, which is Open Gazebo. Yeah, I'm going to click here, and this is going to open the Gazebo window where I should see the simulation. There we go. See, so here I have the simulation with this small environment. Here I can see the LIMO robot, the robot that we are going to be using for today's class. We have already been using this robot also in previous classes. Super cool robot. And then here at the bottom of, at the end of this environment, we have a couple of models, one of an elephant and another of a person standing here, which we are going to be using here for the 3D object detection. Yeah. Okay, so there we go. Here I have my simulation loaded. Then let me stop here for a moment to make sure that everybody has been able to load the simulation. So everybody has been able to properly load their simulation, like me here. Yes, no. Yes, 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 yes. Not yet, Shiva, okay. No, says Chunk. Okay, so for the people who has not loaded the simulation, why not? Are you having any problem, or did you miss some step? Still loading, loading. Okay. It is opened, but I can't see. Show the command again. Yeah, so the command, okay, you should not get it from my stream. Okay, this command and all the others that I'm going to be executing, all the codes, everything, you have it here in the notebook. Okay, here we are currently in the section Start Simulation. After the initial explanations about 3D object detection and YOLO, yeah, section Start Simulation, and then here you have the command that you need to execute into the terminal. Yeah, so all you have to do is to come here, copy the command, and then execute it in the terminal. Okay? I'm going to do it again, okay? I'm going to stop my command, which is going to kill the simulation, okay? And then I'm going to paste it again and execute it again, yeah? But the command, you should copy it here from the notebook, okay? Then, let me execute it again. There we go. And then if you execute the command properly here, after a few seconds, the simulation is going to appear here. Okay. There we go. Okay. Yeah, is it clear? Yeah, Alejandro is showing here a problem, but this is actually not a problem, Alejandro. If you check my output, you are going to very likely see the same message. Let me look for it. Warning. Oh, in this case, I don't have it. Let me see in the previous one. Okay. I don't see it here. So, still loading. Yes, yes, yes. Works. Okay. So for Alejandro, if you're having some problem, just stop the process and execute the command again. Okay? Just execute the command again and it should work. There we go. All right. It works. Okay, excellent. Vladimir is asking, would this work on my local machine? Yes. I mean, this is, well, it depends on your local machine. This is an Ubuntu environment. Okay, so this computer is an Ubuntu computer, which already has ROS installed and some dependencies. Okay, then ROS to Humble. It's based on ROS to Humble. Then it depends on your local computer. Yeah. So every local computer is different and has a different setup. So it's impossible to say, yes, this is going to work perfectly on your local computer, because it depends. It depends on the operating system that you are using. It depends in if you have ROS installed or not, if you have Gazebo installed or not, which version of ROS you have, etc. So we cannot guarantee this, but what I can guarantee is that in this project it works and everybody has this project, okay? All right, then let's continue. Okay, well, yeah, before that, let me drink a little bit. And let me tell you that we have, that in case that you are interested in getting a LIMO robot for real, okay, you can get one from the following link, okay? So this is a super cool robot provided by AgileX, which provides many cool and interesting features like different steering modes, a depth camera, and many more. So very cool robot for personal projects, for educational purposes. So yeah, you can get one here in the following link in case you are interested. And let's get started. Okay, so for this class, we are going to be using YOLO and Darknet for object detection, okay? Now, in this environment, we have already installed Darknet, okay? In case that you want to install it use it in your local computer, then you will need to install also Darknet, and here, in fact, here you have a link to their repository, okay, with the instructions on how to install it and so on, okay? Here in this project, everything is already prepared for you to use it out of the box, okay? So, in fact, if you open the code editor, yeah, which is the second icon down here, besides the web shell icon, you have the code editor icon. If you click here, you are going to open a code editor, graphical code editor, which is going to allow you to see all the folders, workspaces, and everything that is inside this project, okay? Here you can see the Darknet framework installed, okay? And also you have a ROS to workspace, okay, with, for instance, here you have the simulation files for the LIMO and some other testing files and packages, okay? Then, here, as I was saying, you already have Darknet installed and Darknet ROS, which is the ROS package for Darknet, and you can run it with the following command. Yeah, actually, you don't need to be in ROS to workspace. Yeah. So if you copy and paste this command into a terminal, yeah, let me go back to the terminal. And by the way, here you can create new terminals by clicking here in the plus button. Yeah, this is going to open more terminals. We are going to be using some of them here. Yeah, but the important thing is that you don't close the first one, okay? Because the first one is where the simulation is running. So if you close this one, then the simulation is going to die. Yeah. So in order to execute new commands, what we should do is to open a new terminal. So let's open a new terminal, and then here you can execute Darknet, okay? And here you are going to see some debugging messages and so on. Yeah, here you can see how the different layers of the neural network have been loaded, etc. Yeah, and apparently nothing is happening, so you don't see nothing strange appearing here. But actually, so the Darknet system is already running. Yeah, in fact, if we open another terminal and we run, for instance, a ROS to topic list command, we are going to see some topics here that have already appeared, probably related to Darknet, okay? For instance, here, the detector node with detections, yeah? This is a topic which has been generated here by Darknet, okay? However, what we are going to do now is to create our own code in order to be able to visualize the detections made by Darknet, okay? So right now, Darknet is already running, and it's already running its 3D object detection models, okay? So what we are going to do right now, the very first thing that we are going to do is to create a basic program in order to be able to visualize in an easy way these detections, okay? So let's do this. For this, we are going to create a new package where inside our ROS2 workspace, okay? So inside our ROS2 workspace, we are going to create a new package here named 3D object detection, okay? Then we are going to do this all together, okay? So I'm going to go step by step. Then very first step is to, well, let me, for now, I'm going to stop Darknet, okay? Let me organize here my terminals also. So I'm going to rename my first terminal to simulation. Here I have simulation running. Second terminal, I'm going to rename it to Darknet. And the third one, I'm going to use it for visualization, okay? Visualization. Then here in my third terminal, I'm going to move to the source folder of the ROS2 workspace by using the cd command, right? Here, I'm going to execute cd ROS2 workspace src, and then once I am inside the source folder of my ROS2 workspace, I'm going to create my new package using the ROS2 package create command line tool, right? So I'm going to copy this line and paste it here in the terminal, yeah, in order to create my new package, right? So as soon as I execute this command, the new package has been created here, as you can see, 3D object detection. Also, if you go to the code editor, you are going to find your new package here, okay? All right, then let me continue. So once we have our package created, we need to do two things. First of all, we need to update our setup.py file from the package, yeah? So here what you should do is to come to the code editor, open your package files, and here you are going to find one file which is named setup.py. Okay, this setup Python file is the one which defines how to build this package in ROS2. Okay, so here we are going to all you need to do basically is to copy the contents from the notebook. Okay, you copy them and you paste them here into the file. Control C, Control V. Okay, and then basically here what we have is this line here, which is going to generate the executable program from our Python script that we have down here. Okay? So step 1, create the new ROS2 package inside the ROS2 workspace, source folder. Step 2, modify or update the contents of the setup.py file with the ones that are provided here in the notebook. Step number 3, create our Python script. Okay? Where? Here, inside the 3D object detection folder. Okay? Not the first one, which is the package, but the one which is inside the package. Yeah? As you can see, you have two folders with the same name, the 3D object detection. So inside the second one, you are going to create a new Python file with the following name: 3D underscore object underscore detection underscore node.py. Okay, you can copy it also from here, from the notebook. And then here you come to the folder, you right click and select new file. Okay? And then here we are going to put the name of the file. Make sure that you don't have any spaces or anything. And there we go. See? So new Python file has been created here inside my 3D object detection folder alongside this init.py. Yeah? As can be seen also here in the image, in the notebook. Yeah? And then final step is to copy the code from the notebook and paste it into our new empty Python file, like this. Okay? Yeah? And then the final step is to build our new package. Yeah? So we go to the source of the workspace here by executing the cd ROS2 workspace command. And then here we run the callcom build, which is the command used in ROS2 to build a new package. In this case, we are building the new package that we have just created, which is 3D object detection. Yeah? Re-execute this command, which is going to build our package and create the executable from our Python program. Okay? And then, at this point, we are ready to already source the workspace and execute our program. Yeah? In order to execute the program, you have also the command here, ROS2 run 3D object detection node. Okay? Then I'm going to execute this command here. There we go. And then, once I am running the 3D object detection node, what I have to do is to move my robot in order to get closer to the 3D objects to detect, which are these two here, okay? Otherwise, I'm not going to be able to visualize anything, right? Then I'm going to open another terminal here, which I'm going to rename as teleoperation. Rename. And then here I'm going to execute this program, teleop twist keyboard. Okay? This program allows you to move the robot using the keyboard. Okay? Yeah? So here I have the robot in my simulation, and then here, by using the keyboard, let me actually change the view here to a top view so that I can see better my robot, right? So here, by using the keyboard, I can move the robot in the environment, as you can see, yeah? So I'm going to move here to go to the end of this environment, Be careful with the walls and everything, okay, so that you don't crash a lot. It's okay to crash a little bit, but not a lot. There we go. And then move to the end of the environment, as I am doing here, and then rotate and something like this, so that you have in front of the robot the objects to detect, okay? As I am doing right now, yeah? So I have moved the robot closer to the objects to detect, okay? Then at this point, oh, wait, I am missing to run the Darknet, right? So I am running the visualization by not Darknet, okay? So once you are in front of the objects, you can run first the Darknet node, and second, the visualization node that we have just executed, okay? And then we are going to, you should see automatically pop up here the visualization window, okay? Let me wait for a few moments, and there you go, see? This is the visualization window, and here I am able to see the detections right now. As you can see here, it is detecting two things right now, right? It is detecting here a person, and here, I cannot read what it says. Oh, it says it thinks it is a dog. Okay, it thinks it is a dog with a 30% of confidence, yeah? This is actually an error which we are going to solve in a moment, okay? But as you can see here, it's detecting something, but the confidence of the detection system that this is a dog, it's 30%, so it's very low. On the other hand, here it is detecting a person with a 90% of confidence, yeah? So this is okay. This is the output that you should get right now, or something similar, okay? Okay, then at this point I'm going to stop here. So let me come back here. Work it. Okay, I can see some questions here, but you are already answering between yourself. My sim environment got messed up. Okay, just go to the simulation window, Control C, and execute again the command. Okay, you come here, you stop the simulation pressing Control C, and then you launch again the command, and that is going to restart the simulation. As simple as that. Okay. For the rest, have you been able to create the package and execute it and visualize the detections like this? Is everybody been able to follow the example so far? I have no output. Okay, if you have no output, probably it is because you are not looking into the objects. Okay? If your robot and the camera is facing the objects, then you should be able to get the output. Okay? Do we have to edit the local setup bash file? No, you don't have to edit that file. No. Everything that you have to do is explained here. Yeah? Everything. All the steps. Which are create the package, edit the setup.py file, create the 3D object detection node, and that's it. And then you just build. Build and run. Okay? These are the steps. Nothing else. Nothing extra needed. Which type of sensor uses LIMO? It is a depth camera. Okay? It is a depth camera. Salvatore. No executable found. Yeah. A possible reason for that is that you have not sourced it. Yeah. So as you can see here in the instructions, you have to build first, and then you have to source before running. Okay, this is a possible reason. Another possible reason is that you have not edited the setup.file. Yeah, because here is where you are saying, here is where you are generating, adding the instruction, which is this line actually, in order to generate the executable. Yeah. So if you have not updated this setup file, then also you are not generating the executable. Okay. Can we know the distance of the object or their position in the map? Yes, we can. And we are going to do it in a moment, Vladimir. How can I move the robot? Is with this command here. Okay? Everything, again, everything that I am doing is explained in the notebook. Everything, all the steps. Okay? No, Arnut, you are not going to get a window until you move the robot in front of the objects, okay? In any case, if you want to manually open these graphical tools, you can do it here with this icon here, yeah? The graphical tools icon, which appears down here also. Yeah, if you click here, this is going to show you the window, okay? Doesn't seem to be responding to the keyboard commands. That is because you don't have the focus in the terminal, okay? For instance, if you run the teleoperation program, but you don't have the focus here, see, you have the focus in the simulation, nothing is going to happen. So right now I am clicking on the keys, but nothing happens. In order for the program to work, of course, you need to have the focus here in the terminal, yeah? You are going to see the prompt here appearing and disappearing. This means that the focus is not here. If you move the focus somewhere else, then the prompt is going to stop, and then it's not going to work. You have to have the focus here in the terminal, okay? If your focus is here in the terminal, then you are going to be able to move the robot. 100%. Okay, lots of questions, but we need to move forward because otherwise we still have many things to do and we are not going to have time, okay? Guys, in case that you have any problem, go back to the notebook and check, okay? All the steps, everything is explained here, everything, okay? So if you have something wrong, it's because some of these steps, you are missing some step, or you have done some of these steps wrong. So check the notebook and make sure that you are doing everything as explained here, okay? If you do everything as explained in the notebook, then things are going to work, okay? Okay, then let's continue. So now, okay, well, before continuing, let me explain what's going on very quickly, okay? So what is going on here? Let's have a quick review at this program, yeah? So what we are doing here in this program is very simple. So basically, we are creating two subscribers. First of all, we are subscribing to the depth camera. Yeah, we are subscribing to this topic, camera depth image raw. Yeah, so we are subscribing to the image of the depth camera, yeah, the 3D RGBD camera, okay? And also we are subscribing to this topic, detector node detections, okay? This is the topic where Darknet is publishing the detections. Okay? So I am subscribing to these two topics, to the detections by Darknet and to the image that the depth camera is capturing. Yeah, the depth camera of the robot is capturing. Okay, then here I have the callback for the image, yeah, for the first subscriber. Then here what I am doing is I am converting the depth image to a CB-friendly format, okay, using the CB bridge, so that I can better process and manipulate the image, okay? And then, if there are detections, I am calling the overlay detections function, okay? Then, in the detection callback, in the callback for the second subscriber, here what I am doing basically is to save all the detections into this detections variable, yeah? Then what happens here in the overlay detections, yeah? Here what I am doing is to draw the bounding boxes, yeah? So here, basically, I check for detections, yeah? I check for the detections, and for any detection, I am getting the coordinates, and I am drawing a rectangle for the bounding box, okay? And then, additionally to the bounding box, I'm also writing some information. What information? Well, the class ID, so which kind of object I am detecting, which you can see, for instance, here, it is person, and also the confidence, yeah, as you can see here, the confidence, yeah, so the object name and the confidence. Then I am getting the image from here, and I am overlaying to the image the bounding box with the object name and the confidence, yeah, which basically means how confident is Darknet that this person that this object detected is a person. In this case, here it's 93%. Yeah, here now it's showing it's changing all the time. It was showing home and other things. Okay. Yeah. Does it make sense, more or less, this code? Do you understand what we are doing here? Yeah? Yes, yes, yes. Okay, excellent. Then let's continue. So the very next thing I want to do is to filter out these noisy detections. See? So now here it's detecting an aeroplane. This big bounding box, it's saying aeroplane 37%. Okay? Down here it was showing a dog with also over a 20%. Yeah? So what we are going to do is to filter these noisy detections. I just want to keep the detections which are accurate enough. Yeah? Then how are we going to do this? Very easily. We are going to do this by filtering the detections by the confidence score. Yeah? Then let me go back here to the notebook. Yeah? By the way, here you have at the end of the section, besides this brief explanation, you can click here for a more detailed explanation. Okay? I'm going to skip this, but you can check it out later with more time. Okay? If you click here, this is going to open the detailed explanation of what is going on in the code. All right? Then, here what we are going to do is to use the model confidence in order to filter out noisy detections. Yeah? Then, how we are going to do this? By updating this code. Yeah? So, here, what I'm going to do is to copy this detection callback, and I'm going to paste it here into my program, yeah? So as you can see here, we are getting all the detections without doing anything else. So I'm going to remove the current detection callback function, and I'm going to paste... Actually, I need to tabulate here. let me add here there we go. Okay, so here basically what we are doing is to only get the detections where the confidence score is above 0.8, so above 80%, right? I am setting my confidence threshold to 80%. So what's going to happen now? Well, now, if I recompile my package and I run it, I should filter out this aeroplane and this duck that I have here, and only have the person detection remaining. So let's try it out. I'm going to stop my program. I'm going to rebuild it. Very important, you need to rebuild it, okay? Because we have modified here the... Oh, by the way, this doesn't go here neither. This goes here. There we go. Okay, I'm going to rebuild my package. Source and run again. Okay, I'm running again my program, and now we should have the other detections filtered. As you can see, now the only detection that I get here is the person which is above 80% of confidence, in this case 91%. But the other noisy detections are filtered out. Okay? All right. Yeah. If you are not seeing the detections pop up, very likely it is because you have not moved the robot here in front of the models to be detected, which are this elephant and this person, okay? As you can see, my robot, I have moved my robot here in front. If you have the robot somewhere else, then you are not going to have that. As Gilbert is also suggesting, okay? All right, then let's continue. So, okay, so yeah, this is very nice, very cool, but somebody already in the chat, I don't remember who it was, asked, hey, Alberto, but can we know the position of the robot, of the detection? Can we know where the detected object is? Because here in this detection, we are able to detect it in the image, but we cannot tell where it is from the robot, right? So this is what we are going to do right now. And how we are going to do this? Well, we are going to do this by using the camera's intrinsic parameters. Okay? So, how we are going to do this? We are going to do this by updating our code. Okay, we are going to add a piece of code. So the steps are going to be the following. First, we are going to calculate the centroid of the bounding box from the detection. The centroid of the bounding box. Second, we are going to get the depth value from the depth image at the centroid. Third, we are going to convert the 2D image coordinates into the 3D space using the camera intrinsic parameters from this topic, camera depth, camera info. And finally, we are going to display also these 3D coordinates into the OpenCV window here. Okay? Then here, down here, you have the updated code. So what we should do here is to copy the code and replace the one that we have here. Yeah, so we can delete this one and paste the new one. Yeah, and in the new code, you are going to see some additions. For instance, here we have a new subscriber. Yeah, we are subscribing to this topic, camera depth, camera info, in order to get the intrinsic camera data. Then also in the image callback, now we are storing the depth image also. Yeah, so we are getting the depth information for the 3D calculations, okay? This is the same as before, the detection callback. And then here in the overlay detections, we are adding also some new things, right? Specifically here, yeah? Here we are using the depth image in order to get the 3D position, yeah? Using here some formulas, okay? I'm not going to go into detail about these formulas. Again, you have some extended information down here, yeah? If you click here in the detailed breakdown, here you are going to see some more information with the formulas used and so on, okay? But because I am using a depth camera, I have the depth information. So I can use this depth information in order to get the coordinates of the detection, okay? Then, let's rebuild here our package because we have updated the code. Let me rebuild the package, and then now I'm going to source and run again my program, right? There we go. And then now I'm going to see several things here, yeah? So now we have here the bounding box with the centroid in red. We have still the class ID and the confidence score, and down here we also have the coordinates in the X, Y, and Z of the 3D space, okay? Okay, but that is not all. There is one step missing, which is the most important actually for ROS, yeah? Which is publishing ATF to the object, yeah? Because now I have this information, but this information is not so useful, yeah? When working with a ROS system, what we would usually like to do is to have a TF, yeah? Do you know what a TF, a transform, is? Yes, Vladimir. Usually you are going to need a kinematic solver for a manipulator robot, yeah. Okay, so a transform, there is a great course on transforms, Gilbert. Yeah, thank you. We have a very cool course on transforms in our academy. But yeah, basically a transform is the relation between two frames, okay? So what we want to do is to publish a transform which relates, we are going to publish a frame where the person is detected, and then we are going to publish a relation between the camera or our robot and this person. Okay? Actually, let's see a practical example which is going to be much better. Okay? Then, again, we are going to update the code one more time with the one we have here, okay? I am currently in this section, publishing ATF, yeah? So here we have the updated code, right? So let me one more time go back to my code editor, remove the current code, and paste the new one, yeah? And in the new code, you are going to see that we have this publish TF new function, yeah? So basically what this function is doing is that it's getting these coordinates and it's publishing a transform from the camera depth of optical frame, yeah? So from the frame of the camera of the robot, we are publishing a frame into the object name frame. In this case, the object name is person, so we are going to create a new frame named person frame. Okay? How does this look? Let's see, because this is going to be much clearer when we visualize this, okay? So let me rebuild this program. Well, actually, Actually, I'm going to do something. I'm going to show you this before and after. Okay, let me show you the before, and then we are going to see the after also. Because you are going to see the difference. Okay. Source and run. Okay. So this is what we had right now, which is we have the detection here in OpenCV with the information, right? We have the bounding box with the centroid, the information published here, and so on. But we don't have the TF, right? So here, what I'm going to do in another terminal is to start RVs. RVs2. Yeah? RVs2 is this panel that we have, that you can see here in the notebook. Yeah? Then here, which is going to appear also here in the graphical tools. Yeah? So here, what we need to do is, first of all, I'm going to change the frame to base link. Okay, there we go. And then here I'm going to add a point cloud visualization, like this, point cloud 2. Yeah? We add a new display of point cloud 2, and here we need to set the topic name. Yeah? Here the topic name is going to be camera points. Okay? If you click here, it's going to give you already only one option, which is camera points. Okay? And then once you select this, you are going to have the following. Let me zoom in here. So basically, this is very interesting. This is what the point cloud is detecting of the camera. See? And in this case here, you can see the elephant, the point cloud of the elephant, and the point cloud of the person here in 3D, right? This is already in 3-dimensional space, right? The robot is here, okay? And furthermore, we are going to add another display for the TFs, for the transforms, right? Let me add it here, okay? And all these TFs that you can see here are the TFs of the robot, right? Actually, we can select an option here in the TFs to display the names. And also you can right now this is showing all the transforms of the robot, so it's a bit complicated to see anything. I'm going to remove them and leave only the camera depth frame, which is here. All right? Yeah? So this is the frame of the camera. Then what I'm going to do with the new code is create another frame in the person and publish the relation between this frame and the person frame. Yeah? Let me show it to you. So here I'm going to stop my program and update it with the new code that I have here. Let me come here and select the updated code. There we go, copy, paste, right? And here we have the code already for publishing the TF. Right here, yeah, the publish TF method. Okay, then as always, I need to recompile. Source. And run, okay? I'm going to run again my program, and now if I come back here to RVs, you are going to see what happens. What is happening? See? So now, suddenly, a new frame has appeared here where the person is, yeah? So now we have this frame where we are detecting the person, which is related directly to the camera frame. Yeah? So now we know exactly the position and orientation of this person with respect to the robot. Yeah? And we can use this transform in ROS for many things. In this class, for instance, we use this frame in order to approach to the person using this TF. Okay? Yeah? Does it make sense? Let me see the last comments. The frame saves the center of the position. What about the size bounding box of the object? Do we have that? The size of the bounding box. The size of this bounding box, you mean? Yes, you can also have this information for sure. Yeah. This is automatically done. You can see here in the code where when you create the bounding box, which is here. See, so you can get this information of the bounding box. Yeah. Yeah. Okay. Okay, then I'm going to do this last part, okay? Which is to, well, actually, I think I'm going to leave this last part for you guys, okay? So now we have the main part of the class, which is to build the object detection node and to create and to publish the transform to the object. And then the last part here is to create a new package, move towards, well, actually, let me do it very quickly, and then I will let you tune it yourself later, yeah? So here, the last part of the class is to create a new package. Again, you have all the instructions here, okay? And then you need to update, again, the setup.py. I'm going to do it very quickly now, okay? Here we have the new package. I update the setup.py. I have to create a new program, a new Python script here. Let me create it, copy and paste. I create the new Python script here. Okay. And then I copy and paste the code from the notebook. And this code, you are going to see it's very, very basic. Yeah. In this code, here what we are doing is we have a subscriber to the command bell topic, and we create a transform listener. Yeah? What we are going to do is to listen to the transform from camera depth optical frame to the target frame, which in this case is person frame. Yeah? See, the target frame is person frame. So I am getting the information of this transform, the transform from the camera depth optical frame to person frame, and then I use the information of this transform in order to publish a twist message to the command bell topic in order to move the robot towards the detection, right? Very basic program. Again, if you want more details, you can have them here, okay? You have all the explanation here. Then what I'm going to do is to build the code. Let me do that very quickly. And source and run. Actually, I need to source here. Let me stop RVs now. CD ROS to workspace. So here I need to source and run the detection node, which is this one. And in the third terminal, I'm going to run the new program, which is this move towards object node. Yeah? And now we are going to see that the robot is going to start moving here towards the detected object. Yeah, you can see it here moving towards the person. All right? So, yeah. where is this Jupyter Notebook file? It's here. You can open it here in the Jupyter Notebook button, okay? So here in the down menu, you have a button which says Jupyter Notebook. So if you click here, this is going to open the Jupyter Notebook, okay? Yeah? Any questions so far? I'm going to leave it here. We are already quite late. We should have finished the class like 12 minutes ago. Is the guy okay? Vladimir is asking. Well, probably at this point, well, I am crashing against everything, yeah. So this program, the approaching program can be improved. In fact, I suggest you to improve it, okay? Have a look at this program, improve it, and you can try many different things, okay? Here. But yeah, the guy, we have it here. And it seems, yeah, so the robot didn't crash against him. Almost there. So he's chilling here so far. Yeah. Very cool, Gilbert. He says, I already tagged the construct on Twitter with some 3D object detection. Nice. Yeah, so as always, let me finish this class by remembering that these classes are very limited in time, so there are many things that I cannot explain, okay? Here I have left a link in case that you want to learn more about perception in ROS 2. You have here a complete course where you are going to be able to learn these and many, many more things, all right? Here in our complete ROS 2 perception in 5 days course. And as always, in case that you create some nice programs here, as Gilbert has done, please go ahead and share your work with us in our social networks, okay? We always love to see your work and to see our students doing very cool stuff with the material that we provide in these open classes, yeah? So thank you a lot, Gilbert, for doing that and for sharing your work and for being here in almost all our open classes. Very cool. Is possible to use YOLO 9 here? Yes, Pablo, for sure, it is possible. Yeah. Here we are using a smaller version, I think, because of the limited resources in the project. But if you have a powerful enough resources, you can use YOLO V9 without problems, yeah. All right, guys, then, yeah, so I'm going to leave it here. I hope that you enjoyed the class. And, yeah, hope to see you all in the next class. It's going to be next week. Hope to see you all there. And as I always say, take care and keep pushing your robotics learning. Bye-bye.